All right, this better be recording me. I think it is. All right, this might be actually the best problem to start with. I'm going to put that in the notes, this 2012 problem, because we actually can't do part A yet. And so it's only B and C, and they're pretty mild. So I feel like maybe this is the best place to start. So we have the function g has derivatives of all orders, and the Maclaurin series for g is bleh. So Maclaurin just means we're centered at 0. So part A says using the ratio test. That's not a problem we can do yet. So we're not going to do part A. We don't know what oh my goodness. We don't know what the ratio test is yet. So the Maclaurin series for G, evaluated at x equals 1/2, is an alternating series whose terms decrease in absolute value to 0. When I see that phrase, I know they're getting me ready for error, to find error. When they say this series is an alternating series whose terms decrease in absolute value to 0, this tells me I'm going to be using error and that I'm not going to have to use Lagrange. I'm going to be able to use the next term because they're already setting me up for it in the way this is worded. Okay, this approximation for g of 1/2, using the first two non-zero terms of the series, is 17 over 120. Show that this approximation differs from g of 1/2 by less than 1 over 200. So they're asking me to show that the difference between the polynomial which has the first two non-zero terms, so it would be a third degree polynomial, evaluated at 1/2, minus the value of the function at 1/2. Whoops, it's not f, it's g. They're saying, show me that this error, this difference between the polynomial and the function, which they actually want me to use the absolute value of because they want the error to be positive, show that this error is less than 1 over 200. That's what this is asking you to do. It's just a lot of words, so it's really freaky. So when they want me to do this, they want me to just use the next term. I don't have to use Lagrange error bound. I don't know anything about G itself. I don't know anything about its derivatives, so I would never even be able to find that next term using Lagrange. I know I said in the last video something about when we have x's in our series, that tells us we should use Lagrange. Yeah, I do know I said that, but I also know that this is kind of forcing us to plug 1/2 in for x. So this is saying that my polynomial, my third degree polynomial at 1/2, is putting 1/2 over 3 minus 1/2 to the third over 5. They already did the math for us. This ended up equaling 17 over 120. They just didn't want you to have to do the math for that. So they're saying this approximation of these first two terms, which turned out to be a third degree polynomial, is 17 over 120. Let's show that the difference between that polynomial's estimate and the actual value of g of 1/2 is less than 1 over 200. So to find this value of this error, I'm going to use the next term. So I'm going to use up here the next term, evaluated at 1/2. So that error is just going to equal 1/2 to the 5th over 7, which is going to equal 1 over 32 times 7, which is 224. And this is less than 1 over 200. What gives me a clue that I'm on the right track is when I get a number for error that looks a lot like the number they want me to compare it to. So they want me to, if they wanted me to compare it to like 1/10, it wouldn't really make sense, or even 1 over 5,000 or something, it wouldn't really make sense. But to compare it to 1 over 200. Oh yeah, well, mine's just a little bit different. My denominator's a little bit bigger, so my fraction's a little bit smaller. That particular question, this was a 2-point question. They wanted you first to maybe write or understand that you're finding error. So nowhere did it say find the error. That's kind of what they want you to do. And then 1 point for actually finding that number of 1 over 224. So it is what it is. Part C, let's do part C also because we might as well. Find the first 3 non-zero terms and the general term for g prime of x. So this should make us feel better because all we're going to have to do is take a derivative. So this is my series for g. I want the first 3 terms for g prime. Oops. G prime is going to equal the derivative of this, so 1/3, minus the derivative of this, 3x squared over 5, plus the derivative of this, 5x to the 4th over 7. So the first 3 non-zero terms, there they are. And then the general term, we've got an alternator, we've got a fraction. On the bottom of the fraction, I've got odd numbers. On the top of the fraction, I've also got odd numbers. And then the power of x's are even numbers. So let's see, I've got odd numbers over odd numbers, but the odd number on the bottom's bigger. So I'm going to say we have a 2n plus 1 on the top to represent that odd number, and then a 2n plus 3 on the bottom because I've got to go 2 more, and then x to the 2n. So we will start with n being 0 because I don't want to have an x. I want to have a 1 on the top, a 3 on the bottom, and I also want this to be positive, so there we go. That particular part, sadly, is only worth 2 points as well. 1 point for these terms and 1 point for the general term. You get most of your points for part A, which we can't do yet. That'll be coming next. Okay, hopefully that one made more sense. At least letter C hopefully seemed nice and easy.